Hey there! In this video I will show you how to create this Scifi atom model. It's inspired by the Bohr atom model. You've probably seen that. It's the classic 2D illustration where you have the electrons moving around in circles or shells around the protons and the neutrons around the atom core. And so this one is of course a rather loose artistic interpretation, and the goal here was to make it look cool. But nevertheless, you could use this to represent like all the Bohr atom models. This tutorial is aimed at intermediate developers, so you should have a basic understanding of Unity and shaders. I will try to explain everything that I do step by step, why I do it, but some foundational knowledge is definitely required here. Also, just every 10 seconds is a completely new concept. That's just frustrating. Anyhow, if you don't understand anything, just leave a comment below. I will check them from time to time and try to help out. I will be using Amplify Shader Editor, which is similar to Shader Graph, but just overall much better tool to create shaders. If you want to use the same model and textures, you can grab them from my GitHub. That also includes like all the shaders you see here in this tutorial. In the first part of this tutorial, I will show you how to create the stuff that you see in the middle. So that's one shader and usually just two materials, but using that shader. And in the second video, I will show you how to do the wings and the particles moving around in these like sine waves. Now let me show you the basic setup real quick. There's really just one C# script here called core particles. It has a reference to an inner core particle and an outer core particle, so two game objects that I'm using as prefabs. They are inactive here. Each of these game objects has a material of the shader that we're going to create. So they have different ones, right? We have the dark purple ones and the small blue ones. And those objects are just simple spheres. However, they have a relatively high poly count. I think it's like 30 times by 16. And of course, it has to be relatively high because we're doing all these like wobbly transformation, and otherwise it's just going to look pointy and jaggedy. And then I have these buttons and sliders here. So if I want more particles, I can just click the button to create more. And the slider is down how many of these do I want to have active. So that's really just a helper tool. So I can quickly say like, how does it look if I have 10? How does it look if I have like 50 particles and so on. So they just get created as game objects. They get stored in this list up here. And so this makes it working with the shader a lot easier. So here we have the script, right? The transforms that I'm referencing, a list of transforms where I store the ones that I create. And the slider here, where the range attribute makes them go from 0 to 1. And this one is for debugging, just so I see what's the actual total number. Since the slider, that's always relative of how many are in the list. So in the start function, I'm calling this set random position for all the particles. And that is actually really important for the shader to work. Because basically what I'm doing is I'm creating a random seed, so every particle can use their own. That's just a really handy way to not having to actually set a property in the material. And then I would also have to create a new material instance for every single particle. However, I can have access to the world position in the shader, right? And so if I use a tiny random offset, that's actually so small that the user might not even see it. It might literally be on the this pixels on the screen might not change because the offset is so small, but I'm getting all this wonderful random seeds here. And then when we go into our shader, I can just grab all these random seeds. In Amplify Shader Editor, if you use the object to world node and you just leave it unconnected, so the input is 0001, what you get is the current world position of the game object. And then I take one of these components, like here the x, and I multiply it with 1,000. Then I get the floor of that, so the smallest integer, and I subtract that. So what I'm getting now is like all these fractions, right? So here I'm multiplying with 1,000, so I'm getting like 2.4, and I'm subtracting the floor, so that's 2. And what I'm getting is 0.49, and so on. And that means I can also do that with multiplying with 10,000, 100,000, and so on until I run out of digits. And every single one is now going to be a random seed that goes from 0 to 1. I can do that with the x, the y, and the z. So a very handy way to have like 20 different random seeds per particle without having to set them via script. And I could even just grab all the objects, I move them a tiny bit, and now they have completely different seeds. Okay, so now I'm going to explain how to do the offset, and for that I'm just reducing all the values here in the shader. I'm also going to do one at first, so it's a little bit easier to see. I'm going to keep in the color, right? You can probably see there's something going on here. It's based on movement or all that. We're going to do that in the end because it needs all these inputs, but I'm just going to keep it for now because it makes things easier to see. Okay, so first things first, let's just do the scale, and that is quite simple. I take the vertex position and I multiply it with a property called particle scale, and then I store that in a variable. I'm also storing the particle scale in its own variable, and I call this particle scale PT for pass through, because in Amplify Shader Editor, if you take this property node and you duplicate it, what you actually did is you created a whole new property, right? It has this name, particle scale 1. This one's particle scale, well, no number. So that's different from shader graph, where if you were to duplicate the node, you're still using the same property. In Amplify, that's different. And so it's just easier if I need to use that later on, I can have that in a variable. And then we just take these scaled vertices, pass them in the vertex position. And one thing to keep in mind here, I'm using vertex position set to absolute. By default, it's relative, but I find absolute just, depending on the use case, in this one, I find absolute to be easier to work with. To offset the particle in a random direction, we need a completely random vector, and we can just do that by grabbing one of those three random variables that we created earlier. If you remember, they are from 0 to 1, so I want to remap them from -1 to 1. So just subtract 0.5 and multiply with 2. Put them all together in a vector 3, normalize it. So now the direction, the length is 1. And yeah, that's a complete random direction anywhere in the world. And then we take that random vector and just add it to the position of the particle in the world. So this object world node, once again, if you leave the input unconnected and it's 0, 0, 0, 1, you get the position of the particle in the world out of it. And so we just take this one and we add the random vector. And of course, this world position, but our shader wants to know the object position vertices. So we need to transform it from world to object. Then we register it here to the not so well named variable. Probably should have called it like local space. Usually I do that. But yeah, and then we just connect it here. And then we save it. And here I just had like 10 particles, right? They're all in the same spot. So now they all have a random direction. And of course, if I make more of the outer ones active, you see they're all getting offset from the center at the same length at a pretty random looking direction. All right, so let's have some fun with that offset, right? So this one here, random vector, now it has a length of 1, and it's really just do it once, right? There's nothing animated here. So, but we can just multiply that value with some more interesting ones. So here we have the offset wave speed. We passed it just a simple float, pass that into time for the scale, right? It's basically like multiply with v time. And pass this into a sine wave. And of course, sine wave returns -1 to 1. And why not just use a vector 2 so we can remap this to anything we want. So we remap this, and now we have a strength. And now we multiply our strength instead of just passing it once. And now if we save that, offset min max, I had this to 1. So now we make 0 to 1. And now, of course, offset wave speed. Holy smokes. Right. So now they're using the sine wave. And of course, we can play around with the values. And then we can make this a bit faster. And now to not all have them do that at the same time, let's just grab a random one, multiply with something large, right, 100, so it's definitely at a completely different part of the sine wave. Maybe just take the time there, get it out here, multiply it, and we add this before we put this into our sine wave. Now we save that, and yeah, see, this is one of the huge advantages of the random one. Okay, cool. So now they're all moving. Also, one interesting thing to note is now, of course, they're doing the sine wave now, in and out, so they're kind of like slowing down. You could, of course, also just have this one to be a negative. So now they're like at the center, they're at the fastest, right? So you can also get like a nice effect. Okay. Okay, so now let's do the wobbling effect, and for that I'm going to reduce it to one particle and get rid of the animations that we did, so it's a little bit easier to see what's going on. Actually, I'm going to use two particles because once again we need to talk about how to make them all look a little bit different. At the core of this wobbling animation is this 3D noise that we're going to use to determine where and by how much we should offset our vertices. So I'm just going to register this in a variable here that's just for debugging, or rather for explanation here. I put this in the color node. Right now it's gray because the scale is set to 0. We'll fix that in a moment. So 3D noise, as the name suggests, can take 3 inputs and return a random point, or rather random output for like an X, Y, and Z. So we have a sphere, so that's quite handy, right? It says UV here, but of course it's X, Y, and Z, or it would be UV and W. And then, of course, we also need the scale. So I have a new property here called wobble scale. And I divide it by the particle scale. That's the property that I stored in a variable earlier. I'm just doing that so that it stays relative to the particle scale, because you don't want to like have the perfect wobble values and then you make the particles a little bit bigger and now you have to readjust the wobble scale and all of that. And so now we can increase the wobble scale here. And you can probably see, right, it gives us these nice random values. Of course, not totally random because we're getting these nice smooth gradients, like with almost all noise textures. And you can see it maps nicely around a sphere because it's a 3D noise. And now it's quite simple. We want to offset the vertices, the brighter or like the larger the noise value is. So I have this wobble strength property here, and now I multiply it with the particle scale that I was passing through. Once again, the idea is just that it stays relative if I decide to change the particle scale. And then we take the vertex position and we multiply it. And of course, usually when you do vertex deformation, you take the normal, but this is a sphere, so we don't have to do that. We can just take the vertex position X, Y, and Z, multiply it with the wobble strength, this is another property, and of course the output of our 3D noise, and then we register that into this wobble offset variable. And then we take that variable and we add it to the vertex position, and now we have this offset. And so here you can see the larger the value, right, the closer our noise is to 1, the stronger we're getting the offset, and the black dots, this is where we get no offset at all. Okay, so now let's animate that, and all we have to do is make sure that we are sampling different values at different points in time. So I just have this property here for wobble speed. Once again, I multiply it with the particle scale so it stays the same, or rather looks the same when I scale it up. I pass that into a time node, so multiply it with the time. And then we add this to the position that we are sampling from. And also I'm doing here the same what I did with the offset. I just make sure that every particle is like a little bit different point in time. I take the random, multiply it with 100, also add this, so now every particle looks like it's wobbling in a different way. And then of course we can just play around with the values, right? We have the strength, the scale, and the speed at which it is moving, and that should be quite flexible to do all kinds of different effects. Connected the color again, yeah. So let's get back to the color and let's do some rotation. I want to do that first. Where do I have this one? Okay. So for the rotation, to make it look a bit better, I take all of this, right? Basically our final position, the one that you're seeing here now, which means in the end we're going to plug this one in, right? So rotation. Once again, we're going to get a random vector, y1, y2, y3. Those go from 0 to 1. And then we can subtract 0.5, multiply with 2. And I'm just realizing I could have done that for the original vector, which I think I did that in 3 nodes, right? We don't have to normalize it because our rotate about axis has a normalized axis here. That's quite useful. Okay, so we're going to get a total random axis. For the rotation angle, we just pass in the time, right? So I have a rotation speed here. And for the position, this is the one that we just made here, right? All of those 3 together. Pivot point, very important, as I mentioned earlier. I'm assuming that this thing is going to be centered at the vert. So if it's not, then you have to put in a different pivot point here, right? Whatever is the center. And then we rotate this here. And then this is our new position. And yeah, so now these things are rotating. Rotation speed, if I give it some speed, right? So now those things are rotating. And might be a bit better to see. Oops, let's go like this. Go particles. Let's get a few more, and now they're rotating. Okay, last but not least, let's talk about the color. For that, I'm reducing all the movement here, but I'm keeping the wobbling because that is quite important. Okay, so first let me show you the broken way of the Fresnel, and that is we're leaving this node unconnected, which you would normally do if you're using a Fresnel node, but you don't have any vertex deformation. So now that input just assumes the smooth vertex normals that are in the object data. And so the inputs here, I have scale and power. I think that should be enough to get most effects that we want. And then we just do like the standard way where we lerping between the 2 colors where I have a main color, and then wherever I have a Fresnel effect, I just want to use a different color. Let me set those to the colors that you see on the screen so it's a little bit more obvious. So the Fresnel effect is of course all about how perpendicular is a face to our viewing angle. So if we're looking directly at a face, we're getting no Fresnel effect. If it's exactly like 90 degrees, then the effect is quite strong. And as I mentioned, if we leave this node unconnected, it takes the smooth vertices or the smooth vertex normals of the object. However, we are deforming the object, and our Fresnel node doesn't know that. So it's kind of showing us the vertices that are like behind that we aren't really supposed to see. So we need a way to make sure that to tell that Fresnel node we have different normals now. One of the cheapest and quickest ways to do normal reconstruction is to use DDY and DDX. So I'm using like the final vertex positions here, I transform it to the world position, and then DDY and DDX can tell me how much did that change to the pixel on the left or the pixel on the right, or the DDY, the pixel on the top or the pixel below, right? And so it's super useful to get all kinds of effects because it's based on the screen. And then we take the cross product, which is of course when you have 2 vectors. The cross product is the one that is perpendicular to the plane that these 2 vectors create. And that is of course the normal. Then we just normalize it, and now we can plug that into our Fresnel node. And of course you can see now it's not as nicely smooth as taking the smooth vertex normals of the mesh. It's almost like if you create the mesh and you set it to like a flat shading right in your favorite 3D editor, which is hopefully Blender. There are, of course, more complex ways to do normal reconstruction where you actually sample different points on the surface and then you get the, you know how much it changed, so you can calculate the angle. But I think generally you always want to have the simplest solution that gets the job done. And I think unless you need to have this like really big on the screen, you're probably not going to notice this effect, especially if there are a lot of those. And so I think in this case, this should be good enough to have the Fresnel effect working once again. One more cool effect we can do with the Fresnel is change the strength based on how much they are offset from the center, like the entire particle moving in and out of the center. So we remap this from a min-max that we can define in the editor. But since SignMath goes from -1 to 1, we can also remap this to 0 to 1 and store this in a variable. So this one is always going to be 0 when they're at the minimum offset and 1 when they're at the maximum offset, whatever those values are. And then we just have a slider for funnel inside and outside, and we lerp based on that offset. Here I also have a power slider, so might want to have like a really drastic effect or just like a very subtle change. And yeah, then we just multiply that with the funnel. And now when we offset them in and out, we can have all these like cool color changes. And this is it for the first part of this tutorial. I hope you've learned something. As always, if you have a question or comment, feedback, criticism, just leave a comment below. I'll post the link of this project in the description. All right, it's GitHub, just grab it for free, make something cool with it. I always like seeing that. Yeah, of course, liking this video probably helps. And yeah, see you in the next video where we're going to do the wings.